ILD for shear force at LHS of A is. This problem for RHS of A we have already calculated. Now we want to see LHS of A. As I told you earlier, A, B, C, say this is D. L by 4, L by 4. For RHS of A we have already drawn. Once you cut at RHS of A, AB span looks like a simply supported span. So you have to rotate theta A, theta B is equal to 1 by L, and you have drawn one influence line diagram like this. Earlier I have explained to you for a 2 marks question. LHS of RHS of A we have drawn already. At that time LHS of A we didn't draw because LHS of A AC portion behaves like a cantilever. We didn't cover by the time, that was introduction. Now let us see at LHS of A how it behaves. This is ILD for shear force at. This story now we will not write because so many times we have written. Without removing the supports at A and B, where we have to cut? You cut the beam at LHS of A. Now because this is like a free end, it can move up and down, it behaves like a cantilever. See here again, simply supported beam, cut here, left side down, right side up. See, after cutting it, this portion pull it down, right portion lift it up. Now after cutting it, that small piece is right side, this is left piece. Cut, left portion hold it, pull it down by 1, because cantilever you have to push it down by 1 meter, 1 unit, 1. If you try to rotate, say clockwise, this because of support B, it cannot rotate because B is there. So rotation will not work. Even if you want to make mistake also, it's not possible. Then it will not rotate, you have to stop it. So it goes like this. So at LHS of A means when the load moves from C to A, wherever it is, shear force at LHS of A is, suppose 10 kilonewton is there. SM you have studied this one. Suppose a load of 10 kilonewton is there. What is shear force at LHS of A? Stand there, look left. Section left side downward is negative. So minus 10. Same result you will get. 10 into minus 1, minus 10. Supposing that load is here, say 10 kilonewton. At LHS of A, if I want shear force, load is here, load is not there. Stand here, look left, no load, no shear force. So see here, no shear force. Wherever load is there between A to B to D, shear force at LHS of A is 0. That is represented directly here like this. In one paper, this is asked for a 2 marks question. Your task is at LHS of A, if they ask, cut, hold, pull. 2 minutes, 2 marks question, 2 minutes time. So within 10 seconds, you will get 2 marks. Supposing that if they ask shear force at RHS of B, again 4 options they will give you, correct one you have to pick it up. This is ILD for shear force at RHS of B. Now you see, without removing the supports at A and B, where we have to cut? RHS of B. So cut here. Now 2 portions are there. After cutting it, this is the right hand side of cut section. The small thing is the left hand side of cut section. Here also you see, after cutting it, this is the left portion, right portion. After cutting it, right portion, that is left portion. Now right portion you see, cut, hold, lift. Cut, hold, lift. So you have to lift it by 1. Because of the cantilever behavior, it goes up. That's all. These are 2 marks, 2 minutes time. So this one paper they asked this one, another paper they asked this one. Next you see, this is cantilever portions, shear force. Then cantilever portions, how to draw bending moment? Now you see, a train of 2 point loads, 150 kilonewton and 100 kilonewton, spaced 5 meters apart, crosses the beam shown in figure. From left to right, with 100 kilonewton load leading. Maximum hogging bending moment. Now we are asking hogging bending moment. Maximum hogging bending moment, which may occur anywhere. Which may occur anywhere in the beam means you have to select the section also. Okay, and also it is not sagging, it is hogging. So we have loads like this 100, 150, spaced 5 meters apart, and this beam either they give you or they describe the entire diagram. PQ RS. Three meters, 10 meters, 5 meters. As we know here, you have to visualize that as if there is a ground here. Here also ground. In strength of materials, sir might have told you, the hogging bending moment or native bending moments occur when the loads are in the overhang portions. If the loads are in the supported span, it will sag. If load is on the overhang portion, it will hog. Now the point is, which overhang portion shall we keep the loads? This overhang is 3 meters, this overhang is 5 meters. That means if I apply unit load here, 1 into 5 kilonewton meter I will get, but whereas here it is only 3. So you will get maximum hogging bending moment at the overhang whose span is more. So at R. So you have to visualize. At the support R you must draw ILD for bending moment. This is ILD for bending moment at R. What is that process? Without removing the supports at Q and R, assume an imaginary hinge at R and apply unit rotation. When you apply unit rotation, this cannot go down because of support is there. So only this portion will go down like this. This is theta R is equal to 1. The deflected shape of the beam itself is the ILD for bending moment at R. I think this process we don't have tried. Without removing the supports at Q and R, apply Assume an imaginary hinge. Assume an imaginary hinge at R and apply unit rotation. Deflected shape is ILD for bending moment at R. So this is the process. Now the loads are moving. First you will permit, when the loads are moving, first 100 kilonewton is moving. This is the first possibility. When 100 kilonewton is here, 150 will be here, because this is how they are moving, 5 meters. This is first possibility. What's the bending moment at R? Minus 100 into minus 5. This value is minus 5, because 1 into 5, 5. 100 into minus 5, minus 500 kilonewton meter. Minus because hogging. So I can write 500 kilonewton meter hogging. Why I have removed minus? Because minus implies that hogging bending moment. Hogging bending moment 500. I can read like that. Now they ask the driver to move forward. If he comes here, suppose if 100 comes here, 150 will be here. 150, 100. Now what's the bending moment at R? Here you see 100 into minus 5, 150 into 0. Now bending moment at R. This is second possibility. Bending moment at R means 150 into minus 5 plus this is 100 into 0. So you will get minus 750 or otherwise 750 kilonewton meter hogging. So maximum hogging bending moment is 750. So two possibilities we have to check. So this is the answer. Maximum hogging bending moment is, one of the options will be 750. We have 2 minutes time to do this much. Based on the description, draw the diagram. You have to decide which location bending moment, hogging bending moment is maximum. At that point, assume a hinge and rotate. Then the deflected shape you will know. Then first, once you get this side as 100 into 5 only, then push it right side. 150 into 5, 750, that's all. This I have written like this, assuming that you are learning it for the first time. So entire process I have shown. Now when you are revising it, you can skip some of the points that the things that are obvious. We don't have to write in the rough work and waste the time. So obvious things you will cut it off, and whatever is required you answer it. Okay. But first time when you are learning, I have drawn completely how the loading, which load enters first at S, then move further, then who will come to S, then where 100 will go, everything we have shown. But in the exam not required, you don't have to explain neatly to anyone in the rough work. If it is a 20 marks question, we will write everything, stories we will write, but otherwise, then just observe how it goes. First to understand the process, then the speed, question of speed will come then. Okay. Now, sometimes they will give you the influence line diagram. Sometimes what they do is they give you the influence line diagram. You have to detect for what quantity that influence line diagram is drawn. Now you see, like this question will come. Consider the beam ABCD and the ILD. Shown in figure. Influence line diagram belongs to. This point, let us say A, B, C, D. L, this length is also L, but this length is 2L. This is the beam they have given. Also, they have drawn the ILD also. Like this. This is the influence line diagram. In 2 minutes time or say 1 minute time, for which quantity this ILD belongs to. I have explained 3 processes how to draw ILDs. To draw ILD for reaction, remove the support, lift it by 1. See, is there any support got lifted? No. So, it is not ILD for reaction. Then ILD for shear force. Wherever you want to draw ILD for shear force, you must cut the beam and lift the beam such that theta A is equal to theta B is equal to 1 by L, so that at the cut section total ordinate must be 1. Then third one, assume an imaginary hinge and lift the beam by rotate the beam so that the unit rotation you have to rotate so that it will be lifted by AB by L, or same location you apply unit rotation. Now see here, by doing what? You will get this deflected shape of the beam, plus or minus. No support got lifted. If already hinge is there, if I assume a hinge and lift it, it will go like a triangle. So that is also not there. Then to get this diagram, I have to cut here. After cutting it, left portion, actually I am supposed to push it down. So the total ordinate is 1. Instead of pulling it down, he lifted it up by 1. That's all. Maybe for him it is negative. Who knows? So to get this ILD, I must cut, hold, lift by 1. Since cutting is involved, it is ILD for shear force. Since you are cutting it at B, ILD for shear force at B. So this is the explanation. To get the deflected shape, as shown in ILD, we must cut the beam at B and lift it by unit amount. Since cutting is involved at B, it is the ILD for shear force at B. Okay. Now, if at all you want to draw ILD for bending moment at C, say, how the diagram can be drawn? This I remove. If you want to draw ILD for bending moment at C, this also I remove. ILD for bending moment at C. In case they ask, we will draw like this. What is the process? Without removing the support at A, C and D, you have to assume an imaginary hinge at C and apply unit rotation. As in the earlier problem, if you try to rotate, after assuming a hinge, rotate clockwise, this will not rotate clockwise. Even if you try, it will not rotate. because it will bend like a simply supported beam deflection. So curved beam you will get, so not possible. So right side you leave it off. Left side, I have to rotate this way only because it should go down. So rotate like this way. Okay. Now this theta c must be 1. Why anti-clockwise we are rotating is it should go down. This value is L. In one paper, they simply asked what is ILD for bend moment at C. Another paper, a load of 4 kilonewton is moving from left to right. What is the maximum bend moment at C? Then first you have to draw this ILD. Then due to 4 kilonewton, if it is moving, say, you must keep the load here, if at all it is moving, some 4 kilonewton, something like that, 4 into L, or if length is say 2 meters, 4 into 2, like that. So this is the ILD for bend moment at C. Now, when moments are moving, or you can also draw influence line diagrams when a unit moment is moving, that is an imaginary load only. That means when a moment, when it is acting at different locations, how that moment influences the reaction or shear force or bending moment. Okay. Now, we'll see when a unit moment is moving from one end to the other end of a structure, how the reaction, shear force, bending moment will be influenced because of the movement of the moment. Actually, moment will not move. We want to know for different locations of moment, if at all it is acting, then how the reaction changes or how the bend moment changes we want to observe. Before writing that, how a moment, when a moment M is acting, how the reactions, how the shear force and how the bend moment goes, let us observe from the strength of materials. We just revise what we have done. This is what you have studied from strength of materials. Assume that you have a simply supported beam subjected to a moment M. This is not a reaction, it is applied moment. We have applied a moment M at A. Because of this M, we want to see what the reactions are. When a moment M is clockwise, then the reaction here and here, two reactions will develop and those two reactions will form a couple. The only effect of this couple is moment. So if this is clockwise, anti-clockwise moment will develop. VA is equal to M by L. VB is also M by L. Now VA and VB will form a couple. A pair of equal, oppositely directed, non-collinear forces will form a couple. The only effect of this couple is moment given by any force into distance. So M by L into L is M. So that's how the reactions are found. If this is clockwise, it should be anti-clockwise. See how your fingers are moving, here down, here up. So this is your anti-clockwise couple. For this one, if you draw the bend moment diagram, we have learned how to draw the bend moment diagram. What is the shape of the bend moment diagram? Is it a rectangle or a trapezium? That's we have studied that if at all I want to find bending moment at B, your first task is you have to stand there, look one side. Instead of looking left side, we can see right side, no load. So bend moment at B must be 0. But if you want to see left side, say there are two forces, plus m minus m by L into L. Again it is 0. Plus m minus m is 0. Instead of writing plus m minus m by L into L is equal to 0 and wasting the time, I can see right side. We are sure that we will get the same result whether we see left side or right side. So whichever side is easier, that side we have to see and find the bending moment. Bending moment means unbalanced moments of all forces acting only on one side of the section. If you see both sides, what you get is sigma m, summation of moments of all forces. That is called external effects of the moments. Naturally, it has to be 0. Only one side you see bending moment. Similarly, if you see a bar is there subjected to 10 forces, let us say, and it's in equilibrium. If you see both sides of the section at any section, both sides of the section, if you see, what you get is sigma x is equal to 0. If you see only one side, what you get is axial force acting on the section. Then shear force, same thing. At any section, you want to find shear force, say. Stand there, look only one side. Unbalanced transverse forces, sum of the forces, is called shear force. Both sides, if you see, right side, left side, then what you get is sigma y is equal to 0. That is vertical equilibrium you will get. Axial force is sigma x 0. That's what you have learned in strength of materials. First chapter, sigma x 0, sigma y 0, sigma m 0 you have written. Then to find axial force means look only one side. If you want to find shear force, again stand there, look only one side. You want to find bending moment, stand there, look only one side. Then you will get bending moment. Now stand here, look only one side. Your choice to see left side or right side. I will see right side, I will say bending moment is 0. Next, exactly at A, actually how to apply the moment M. Strength of materials you have studied that to this member AB, you have to weld a small piece, a stub type thing, you have to weld it. On that you have to apply the force. And that force will produce some moment at A. So that is moment acting in the beam at A, not on the pin. On the pin, it cannot take any moment. On the pin, I told you there is a pin here. On the pin, if at all you apply moment, the pin simply rotates like a shaft. That M is not applied on the pin, applied on the beam. How to apply? SM you have studied. See, that means this is beam, let us say. Here, to the beam, you have to weld a small member like this. To this member, you have applied a more force P may be there, P into D. So, P into D is the moment acting here, not on the pin. On the pin moment, at the pin moment is 0 only because it cannot take any moment. Just to the right hand side, you applied some moment M on the beam. So that's why it is called applied moment on the beam. Okay. Now you see, stand here just to look left side because exactly on the moment you cannot stand and find moment. When you stand on the moment itself, exactly at A moment M is acting like this, say. Then if you put your leg on that moment itself, you do not know under your leg how much movement is there, whether M is there, 10M is there. Then if you see right side one movement you will get, left side another movement you will get. That is not called bending moment. Whether you see right side or left side, you should get the same value. That's what you have studied. So you have to stand here, just to the right hand side of A. Now you have a choice to left or right. If you see right side, M by L into L, M. You don't want to see right side, you can see left side. Stand here, look left, again M. You cannot stand here and see right side, section right side clockwise movement M, and it will hog, you cannot tell. Why? If you stand here and try to find bending moment, what will happen? If you stand here, you will fall down. When you are falling down, whether that fellow produces positive bending moment or negative bending moment, you cannot worry. First of all, this movement M is not bending anybody in air. A moment M cannot bend anyone in air. Whom will it bend? So bending moment will not exist in air. That's what I told you earlier. So you have to stand here, look left or right. So section left side clockwise M, that is plus M, bending moment. Now it is 0. Now you find that it looks like a triangle. This is the bend moment diagram. Supposing that I want to know how the influence of M on the reactions, on the bending moment when I apply at center. Let us say this is the beam. Now I will apply a moment M at center, exactly at center, A, B and C. Let us say this length is L by 2, L by 2. Now what are the reactions? If you see the reaction, again clockwise moment M, then VA is M by L, VB is also M by L. Now let us say we want to draw the bending moment diagram. Bending moment at B is 0 because I will stand here, look right side. Bending moment at A is also 0. Now I will stand here, I will look left side. No moment. Bending moment at C, indeterminate. You cannot find. Exactly under couple, bending moment is indeterminate. That's when strength of materials you have studied. Bending moment at LHS of C, bending moment at RHS of C, but not at C. Now, if you want to find bending moment at RHS of C, this is what you have learnt. Bending moment at RHS of C. How to find that? Stand at RHS of C and look right. So stand at RHS of C, look right side. Only one force is there. Upward forces always give positive bending moment. So plus M by L into L by 2. You will get plus M by 2. Plus M by 2 means somewhere here. This is bending moment at just to the right hand side of C. Now bending moment at LHS of C. Now stand at LHS of C. Again now you can look right side. Don't want you can look left side. So bending moment at LHS of C. So stand at LHS of C and look right. What you will get? Stand here, look right side. How many forces are there now? VB and M. Upward force or positive bending moment. So plus M by L into L by 2 is over. Now you are standing here. To the section right side there is a clockwise movement. So section right side clockwise it will hog. So minus M. So you will get minus M by 2. So bending moment at RHS of C, LHS of the difference is maybe 0.01 mm. So in that also plus M by 2 to minus M by 2, it varies some fashion, let us say. Then that variation, this width may be say 5 mm. Now you are within that 5 mm, you are taking a section at 1 mm from C or 2 mm, 3 mm, 4 mm, 5 mm, we don't know. In that 5 mm range, it will change from plus M by 2 to minus M by 2. So we write as if we take as if because this section is very small, we simply write a vertical line. In this small zone, how it varies, we do not know. Then we will write it a small inclined line because the thickness is so distance is so small that a pen thickness itself is sufficient. So here it is 0. This is minus. This is plus. M by 2, M by 2. This is the bending moment diagram. This is what you have studied. Now you see, overall observations are like this. Two effects I told you of a force, external effect of a force, internal effect of a force. External effect of a force means or a movement means you have to come outside the structure and observe. That is external effect. Internal effect means within the body you have to go and see that. So when you apply a moment m, what's the reaction? M by L, M by L. Pluck it, attach it center. Again reactions are same. Reaction means the equilibrium effect is same. That means the external effect of a couple remains same when it is replaced anywhere in its plane, or when it is shifted to a parallel plane, or when it is replaced by another couple. As long as f into d or p into d is equal to p1 into d1, I can replace it with another couple also. So that's what it means. So a moment m can be replaced anywhere in its plane. Its external effect remains the same. Means reactions are same, m by l here, m by l here. Now internal effect, which you studied in strength of materials. Internal effect of a moment means bending moment. What is internal effect? Is it totally different? Here bending moment is like this, bending moment goes like this. So if you are calculating the external effect of a couple, wherever you replace it, effect is same, but internal effect may be different. That's first observation. Second point is, when you apply point load, when a unit load is moving, say point load, then you have to keep at center to get maximum bending moment. WL by 4 you calculated. But when a moment is acting, you have to apply that moment at the support. Then bending moment is maximum at the support. How much? M itself. Wherever you keep the moment M, then that M will be shared by two sides. This will take M by 2, this will take M by 2. Put together M, we should not tell. Maximum bending moment in this case is M by 2 only. As you can see, right side or left side, M by 2 is the bending moment, maximum bending moment. That means if at all you visualize that a moment M is moving from one end to the other end, the absolute maximum bending moment will occur when the moment is at the support. Its magnitude is M. Also, one more observation is that exactly under a couple, bending moment is indeterminate. That's why we needed to find LHS of C, RHS of C, but not at C. Okay. With these observations, now we can take the influence line diagram. Okay. So these conclusions we'll write here. First one, the external effect of a couple remains same when it is replaced anywhere in its plane. That is, support reactions are same, but internal effect may be different. That is, bending moment diagram may be different. That's the first observation. Once one of the civil services they asked that observation. Now, second point. Exactly under a couple, bending moment is not defined, or we can say indeterminate. That's why we calculated bending moment at LHS of C and RHS of C, but not at C. Okay, this from strength of material, sir might have told you already. Next, third point. If you, this one, when a moment capital M is moving from left to right, absolute maximum bending moment occurs when it is at this support. Its magnitude is M. Absolute maximum positive bending moment magnitude is M. Okay. Now, with this fundamental understanding of a couple, now let us assume that a couple or a unit moment is moving from one end to the other end. How that unit moment influences reaction, shear force, bending moment. Now let us see the question. A unit moment means magnitude of moment is 1. A unit moment magnitude of moment is 1 and has no units. That's a simply 1. That's all. Is moving from left to right of a simply supported beam of span L of span 8 meters. Beam of span 8 meters. Draw ILD for VA, VB, shear force at C and bending moment at C. So, in the exam, here I am drawing 4 quantities VA, VB, shear force, bending moment. But in the exam, in 2 minutes time, you have to draw only one quantity. Means you have to take only one quantity. So, this is the beam, let us assume. This point, let us say A, B. This somewhere here C is there, 3 meters. This let us say 5 meters. Now, a moment m is moving from left to right, you will show like this. Simply 1. This is the moment. Right side arrow mark is the direction. It's moving from left to right, is a clockwise movement. This is a clockwise movement moving from left to right, whose magnitude is 1 and it has no units. Now when it is moving, that means when it is at different locations, how it is influencing the reactions at A, B, how it influences shear force at C and bend moment at C. Now if this is clockwise movement 1, now reaction just now we have taken VA is equal to m by L, m is 1, L is 8, 1 by 8 meter power minus 1. Similarly VB is 1 by 8 meter power minus 1. This will form a couple whose magnitude is 1 by 8 meter power minus 1 into 8 meters. So, meter power minus 1 into meter cancels out, 1 by 8 into 8 is 1 and that has no units. So, now this reaction has units of meter power minus 1. That means this is some imaginary load. Okay. Now, how to draw the reaction ILD for the reaction? When a moment m is here, VA is 1 by 8. When the moment is here, just now you have seen for all, whether moment is at the support or at center, reaction at A is m by L. So, it did not change. Now, when the moment is here also, reaction is 1 by 8. That means for all positions of moving moment, VA is constant 1 by 8. That means your influence line diagram is a rectangle because the ordinates must be constant. So, diagram looks like a rectangle. So, this is 1 by 8 meter power minus 1. Reaction is downward, so we take it as minus. This is also 1 by 8 meter power minus 1. This is influence line diagram for vertical reaction at A. Now, ILD for VB. Wherever moment is there, VB is upward, constant. So, again this reaction is same, but it is plus. This is 1 by 8 meter power minus 1. This is also same. This is ILD for VB. Now, influence line diagram for shear force at C. If you want to draw ILD for shear force at C, when moment is here, say, now stand here, you can look left side or right side, your choice. Now, we want to see right side, say, section right side upward, negative shear minus VB, right side upward means negative, so minus VB. When the moment comes here, still you can see right side only because this is the moment, but we are writing sigma y. That means the unbalanced vertical force. So, moment whether it is there or not, it has no influence on the shear force. That is what you have studied in strength of materials also. So, when moment is here, again stand here, look right side only. Section right side upward minus VB. That means wherever moment is there, shear force at C is minus VB. We know how to draw VB 1 by 8. Now put it minus 1 by 8. So, you will get like this. This is minus 1 by 8 meter power minus 1. This is your ILD for shear force at C. For all positions same you will get. This is also 1 by 8 meter power minus 1. Now we want to draw ILD for bending moment at C. These 3 points, whatever I talked, we will write here. First one is ILD for VA. For all positions of unit moment, VA is equal to minus 1 by 8 meter power minus 1 constant. So, draw ILD for VA as a rectangle. As a rectangle as shown in figure. Next, ILD for VB. For all positions of unit moment, VB is equal to plus 1 by 8 meter power minus 1, again constant. So, draw ILD for VB as a rectangle. Next, ILD for shear force at C. Again, for all positions of unit moment, shear force at C means what? Stand at C and look right. You will get stand at C, look right means minus VB. So, draw ILD for minus VB. It is the ILD for shear force at C also. Next, ILD for bending moment at C. Now come to this one, ILD for bending moment at C. When moment is here, if you want to find bending moment at C, if I see left side, I have to deal with the 1 and 1 by 8. So, stand here, look right side. Upward forces will give positive moment, 1 by 8 into 5. So, you will get 5 by 8, that's all, no units. Because meter power minus 1 into meters, no units. So, 5 by 8 you will get. Wherever this moment is there between A to C, I will stand here, look right side, 1 by 8 into 5. That means 5 by 8 constant. So, first point is when unit moment is somewhere between A and C. Somewhere between A and C. Now, bending moment at C if I want to find, stand at C and look right. So, you have plus VB into 5. So, plus VB is 1 by 8 meter power minus 1 into 5 meters. So, you will get 5 by 8. This 5 by 8 is constant. So, if at all 5L by 8 or 5X by 8 you get it, say, then it varies linearly, something like that could have written. Simply 5 by 8 you got. That means wherever moment is there between A and C, simply 5 by 8 is the moment at C. So, draw ILD as a rectangle between A and C. Between A and C as shown in figure. How to draw that? Now come to this one. 5 by 8 means like this. This is 5 by 8, 5 by 8. Plus you got it. So up to here it is constant. Now if the moment is anywhere between C and B, say somewhere here. Now stand here, look left. Now downward force only 1. This moment has gone here. So 1 by 8 into 3. So 3 by 8. But it is minus because downward force is always give negative bending moment. So minus 3 by 8. That you have to get it. You have to write like this. This way. For all positions it is same. 3 by 8, 3 by 8. So this is ILD for bending moment at C. This will write here. This is the what I said. When unit moment is somewhere between C and B, now bending moment at C is stand at C and look left. Now when you stand at C, look left, there is only one downward force, minus VA into 3. So minus 1 by 8 meter power minus 1 into 3 meters. So you will get minus 3 by 8, and minus 3 by 8 is constant. So draw ILD as a rectangle between C and B. As shown in figure. So like that. So 4 quantities we have drawn, but in the exam they ask you what is ILD for bending moment at C. 4 options they give, 2 rectangles is the correct one. Or they can ask you what is ILD for VA. Even if you have one of the gate papers, they asked it as a 2 marks question. One overhanging beam was there, singly overhanging beam, a moment is moving. And what is ILD for VA? As I have told you, for all positions of the moment, VA is constant. So one big rectangle you have to see and select it. That's all. You have 2 minutes time. You can complete in 5 seconds or 10 seconds time itself. Whatever time is left out, you solve it. You use it for other problems. Okay. Now we'll see how to draw. This is like introduction only. Now how to draw influence line diagrams for members of the forces in the members of statically determinate trusses. Because it is a statically determinate truss, forces in the members of the trusses influence line diagrams also must be straight lines. Means linear variations only should be there. Now let us see how to draw influence line diagrams for forces in the members of trusses. Influence line diagrams for forces in the members of statically determinate trusses. For this also we can use the Muller's principle. When a moment is moving also we can use Muller's principle, but using Muller's principle will give you very big expressions which are much tougher than our simplified strength of materials approach. If Muller's principle lets us finish off in 10 seconds time, 15 seconds time say, then we use that. If he wastes a lot of time, then we go for our ordinary strength of materials approach itself. Do whatever we want, we don't want to spend more than 30 seconds time in the exam. So here also determinate trusses, we don't use Muller's principle because you have to cut the member, give an imaginary displacement, then the deflected shape we have to find, and textbooks if you see very lengthy formulas are given, but you have only 1 minute time, we cannot remember all such formulas for each member. So we use method of sections which will let you complete in 20 or 30 seconds time itself. So easy for us to use method of sections itself to draw ILD for forces in the members of trusses. Okay. Now concepts. Now you see, if you have a truss like this say, this is actually a bridge truss, we can take it. Here you have to visualize that there is a ground, here also ground. This is, as I told you earlier, it is a N-type truss or Pratt truss. Okay. Now this point, say V1, V2, this is your truss bridge or bridge truss. As I told you, beam and trusses have come from the beams only. For small spans, beams we use. For large spans, that beam is replaced by a truss which will act as a beam only. Because beam action is transferred as truss action, means all top chord members are under compression, bottom members are under tension. That means bending tensile stress now transferred as axial tensile stress. Shear force is resisted by vertical members, diagonal members. So only thing is that in a beam you have a solid rectangular cross section, something like that. We don't want to waste money on solid section, because when one member, one wire can make or can manage the stresses or shear force, why should you have a solid rectangular section? Solid rectangular section, if you have 600 mm or 60 centimeters say, you can have here 4 meters also. So you can increase the depth of the beam to 4 meters, everywhere holes. Then weight of the beam is less. Individual members are subjected to axial forces only and resist the shear force, which we wanted to call it as panel shear, because beam shear is now transferred as panel shear. So that's how for larger spans without any intermediate columns, we can go for the truss bridges. Okay. Now you assume that if you have small span, means when a canal is flowing, canal span maybe say 3 meters or 5 meters like that. Now beams you have provided. Now don't assume a canal, assume that a river is flowing. On the two banks of the river, you construct two piers, then trusses. A single truss we cannot use, two trusses must be there. On a single truss, we cannot keep a railway track if trains are moving, let us say. So two trusses must be there. So actually these are two trusses. Now One truss here, another truss may be at a distance of 5 meters, two trusses will be there. Between the trusses, you have to connect cross girders like this. Only at the joints, cross girders will be run. On the cross girders, we keep stringer beams. The beams which interconnect the cross girders, we call them as stringer beams. Those stringer beams, we also call it as in the beams, beams supporting the waste slab. In RCC, you call it as stringer beams. In the staircase slab, we call it as waste slab. One floor to the other floor, when the steps are going, say, you have to have a one waste slab. Waste slab must rest on the two beams, and those beams we call them as stringer beams. In steel structures, the cross girders are there like this. Between the cross girders, we keep the stringer beams. On top of the stringer beams, we keep the sleepers. On top of the sleepers, we keep the two rails. That means railway track. On top of the railway track, trains move forward, backward. So, for the train to move, you have to have two rails. For the two rails to rest comfortably, you must have two trusses. Between the trusses only cross girders will be there. On top of that, uh, stringer beams, sleepers, then rails. Why so much arrangement? Cross girder, stringer beams, then sleepers, then rails. Without that, simply you keep a rail, say. Then because of the train load, rails are so flexible that they will bend and trains will collapse. So for that sake, to increase the stiffness, to reduce the deflections in the rails, so much arrangement is required. Okay. Now as the trains are moving or wheels are moving from one end to the other end of the bridge, how the forces in the members change. If that variation or that influence, if you draw as a graph, we call it as influence line diagram for that force in that member. Okay. If you see this in the top view, the two trusses, stringer beam, cross girders, etc., those things will look now like this. This is one, two trusses, they will go like this. This is truss 1, let us call it. Truss 1, this is truss 2. And they are interconnected by cross girders like this. Say, these are called cross girders. And on top of the cross girders, we run the stringer beams. This is called stringer beam. Stringer beam 1, this is stringer beam 2. On top of the stringer beams, we have to keep the sleepers. Those sleepers will run like this. You see, those sleepers will not touch the trusses. These are called now sleepers. Now they are pre-stressed concrete sleepers we use. Now on top of the sleepers will run the rails. This is rail 1, rail 2. This is rail 2. If it is a broad gauge railway track, the distance between these two is 1.616 meters. So now the rails rest on sleepers, sleepers rest on stringer beams, stringer beams rest on cross girders, cross girders rest on the two trusses, trusses rest on the piers, piers transfer load to the soil. So that's how the load arrangement. Now when we show a unit load is moving on the truss, means supposing that something like that I show, as a unit load is moving on the truss from one end to the other end, you draw the influence line diagram. That means when we show one like this, it looks as if it is resting on the truss member, but trains will not move on the truss members. If goes like this, again train cannot go like this and move. Trains move on the rails only. So trains move here on the rails. So on the rail, as a unit load is moving from one end to the other end, how the force in the members change. Now in this diagram, that circle what I am showing say here, exactly at center, one set of wheels run here, another set of wheels run here. Two sets of wheels. So one set of wheel is for this truss, another set of wheel is another truss. So cut here, throw this piece out. Half thing we remove, only half we will take it. So when the load is, we also assume that the rails are simply supported, but actually they are continuous. The cross girder span, let us say, cross girder spacing is say 3 meters, but rails you can have 10-meter span rails also. But for simplified analysis, you will assume that the rails are simply supported on cross girders. So when the unit load is here, say, because the rail is simply supported on cross girders, half the load comes to this cross girder, remaining half goes here. No load is transferred to the other span. That means when load is exactly at center, say, half the load is coming here, half the load comes here. Nothing will be transferred to this cross girder because it is simply supported is the assumption. If the unit load comes here, say entire load is transferred to the single cross girder only. As load is moving on this cross girder here, because cross girder is here and here, on the on the rail when the load is moving, if this load is say 3/4 of this L, then here you will get 0.75, here you will get 0.75, here you will get 0.25, like that. So through the cross girders only, the wheel loads are transferred to the trusses. So when the load is here, actually it is on the rail. When load is there, it is transferred to the two cross girders, 0.5, zero point 0.5. Those cross girders in turn transfer load to the truss. You see, truss behavior didn't disturb. So entire, if you see the truss bridges, other than the cross girder locations, nowhere the entire system is connected to the trusses. Only cross girders take entire train load and transfer to the truss joints. Now our task is, when the unit load is moving from one end to the other end of the rail, how the force in the members of the trusses change, or how the force in the members are getting influenced. If you plot it, that is called influence line diagram for force in the member of a truss. So this is our conclusion. This is the top view, plan view. What I have shown is the plan view. If you see the truss bridge from top, two trusses look like two lines only, cross girders, sleepers also you can see. From this view, you cannot see the sleepers, just above that one horizontal line we have to show. So this is your conclusion. As a unit load moves on the rail, forces or forces in the members of the truss, members of the truss continuously change. If we plot the variation of force in any member as the unit load moves from one end to the other end of the rail. One end to the other end of rail, it is called influence line diagram for force in that member. Okay, such influence line diagrams we want to draw for the Pratt truss, Warren truss. In the exam, any one truss they give you, one force in the member, in 2 minutes time you have to tick the correct ILD. Let us see how to build them in 1 minute time, and another 1 minute you can use it for some other purposes. And here also first we will explain completely, next we will see what exactly is to be written in the exam. Draw ILDs for forces in the members of Pratt truss or N-type truss. N-type truss shown in figure. Now see, this is one Pratt truss. One, two, three. 6 panels are there, let us say, and it is a, this is the N-type truss because it is in the shape of N. This is in the reverse direction we have connected, let us say. This is the ground. The upper chord members, you use the notation U like this. U means upper chord 1, 2, 3, 4, 5, 6, 7. Lower chord joints, you mention them by L1. L stands for lower one. L3, L4, L5, L6. This is a L7. There are 6 panels now, 6 panels at 4 meters. So total length is say 24 meters. Height also let us say 4 meters. So now this is a 24-meter span of a bridge truss. As the load is moving from one end to the other end, how forces in the members change? We want to plot. Okay. Now we want to first plot say U3, U4. Force in the member U3, U4. As the load is moving from one end to the other end, how U3, U4 changes. So if I want to draw ILD for F U3, U4, you must cut it by a section 1, 1 like this. Unit load you keep somewhere here. It can be anywhere. One by one, let us see. We split the problem into 3 parts. First part is, this is the disturbed panel. When you are cutting it by 1, 1, 2, third panel got disturbed. So don't keep the load on the disturbed panel. What happens is, if you keep on the disturbed panel on the rail, part of the load goes to L3, the remaining part goes to L4. Supposing that load is at a distance of x here say, then this will be L minus x by L, x by L. So like that reactions, that means part of the load comes on both sides of 1, 1. In method of sections, what we do, we will cut it. When the load is here, we will throw it out, we will consider that portion. When I am considering this one, again part of load comes here say, then I have to deal with that headache also. Just to avoid the headache, we will not keep the load on the disturbed panel. Keep anywhere between L1 to L3. What is advantage? If I keep 1 here, part of the load goes to L2. Suppose center of L2, L3 unit load is there say. 0.5 goes here, 0.5 goes here, but nothing goes to right side of 1, 1. So when the load is here, I can cut it. When I throw it out, nothing goes, no part of this load is on this one. Headache is gone. You can get a quick hours within stipulated time, you can complete the problem. So first is, you keep the load somewhere between L1 and L3. Then how we know how to use method of sections to find force in U3, U4. Find that, then that expression will tell you how ILD should be drawn. It must be straight line because it is a statically determinate truss. Second part, keep the unit load somewhere between L4 and L7. So not in the disturbed span, somewhere here, L4 to L7. Then look left side, find force in the member U3, U4. Then that will give you how the ILD goes. Then in the last one, in the disturbed panel, you simply connect it by a straight line because it has no other choice. It must vary linearly only. So 3 phases we will make it. This is what we will make it. ILD for F, this is the first one. ILD for F, U3, U4. What we have done? Cut it by 1, 1. Case 1. First problem we will write completely. Next problems onwards, we will not write the story and waste the time. When unit load is somewhere between L1 and L3. Now, we will consider when load is between L1 and L3, you will see right side of 1, 1. Consider equilibrium of RHS of 1 1 to find F U3 U4. Then you see here, so keep arrows on right side of 1 1 only. So keep arrow marks on RHS of 1 1 only. Now let us see. Come here. When the load is here, cut here, look right side. This reaction, let us say V2. This reaction, let us say V1. Load is here, cut, look right side. These two are unwanted members, L3, L4, L3, L4, U3, L4, we don't want to deal. These unwanted members are meeting at L4. So if I take moments of all force about L4, these two will meet at L4, headache is gone. They give zero moment. So only this we will get it. Now to fix the correct arrow mark, cut here, look right side. Travel from tail to the head towards L4. This is anti-clockwise. To balance anti-clockwise movement, it should be clockwise. So arrow mark must be like this. F U3, U4. See here, after cutting it, travel from tail to the head towards L4, clockwise, anti-clockwise. So we will write here, take moments of all force about L4. Clockwise positive, anti-clockwise negative. So minus V2 into, see here, 4 plus 4, 8 plus 4, 12. Minus V2 into 12 plus F U3 U4 into 4 must be equal to 0. So you will get F U3 U4 is equal to 3V2. Arrow mark is towards the joint. So compression. So for any specific force in the specific location, F U3 U4 is 3V2. But we don't want a specific location, ILD we want. So if I want to draw ILD for FU3 U4, draw ILD for 3V2. That ILD for 3V2 is valid when the load is between L1 and L3 only. So if I want to draw ILD for FU3 U4, I have to draw ILD for 3V2. So draw ILD for 3V2 and consider between L1 and L3 only, because between that locations only this 3V2 ILD is valid. Now come to this one. Compression we can draw below reference line. Okay. So ILD for 3V2 means we know how to draw ILD for 3V2. V2 we know how to draw. To draw ILD for V2, remove the support, hold it, lift it by 1. Don't lift it by 1, lift it by 3 units or push it down by 3 units. Then you will get ILD for U3, U4. So ILD for 3V2 will go something now like this. ILD for V2 means 1. ILD for 3V2 means 3. 3 into 1. But out of this one, up to here only it is valid. So compression will take minus, tension will take positive. But this ILD is not valid, so we cannot show this one. Out of this 3V2 ILD, this only is useful ILD. Other things you cannot apply because for those locations, this 3V2 is not valid. So valid things only we will take it. Okay. Now, after this, we will ask the driver of this load. Assume that there is a driver in that and he is moving right side. Now keep that load here, somewhere between L4 and L7. When the load is here, cut here, look left side, because this is gone there. V1 into 4 plus 4, 8 plus 4, 12. Because again I can take moments about L4. Whatever side you take it, I told you in the equilibrium equations, moment center can be anywhere in air also. Because about that point in air, you are not calculating bending moment, simply rotational effect of that force you are calculating. So you can take anywhere in air. But if you want to find bending moment at a section, there must be a beam. There must be someone to bend. So, case 2. When unit load is somewhere between L4 and L7. So, we will consider, we will take equilibrium of LHS of 1, 1. Again take moments of all force about L4. Clockwise positive, anti-clockwise negative. Now you see, this V1, when I cut here, look left side. Look left side. These two are the members which we don't want, but these two are meeting somewhere in here. That means I am cutting it, throwing this out. That this is no longer is available to us. Now, but these two will meet somewhere in air at L4. So, this V1 travel from tail to the head towards L4. So, V1 into 12 clockwise. To balance it, these two are useless. Now, this only should help. So, this arrow now should go like this. F, U3, U4. Now, this problem is over. This is, instead of drawing a separate truss and solving a fresh problem and wasting the time, here only we are managing it, that's all. This red color arrow mark is for an independent problem. Somewhere load was there, you are starting afresh. So, tail to the head towards L4 clockwise, this is anti-clockwise. So, no question of changing the sign. So, compressive force again arrow mark. So, when I take this one, sigma ml4 is equal to 0 plus V1 into 12 minus FU3 U4 into 4 is equal to 0. So, FU3 U4 you will get 3V1 compression. So, draw ILD for 3V1 and consider between L4 and L7 only. When now come to this problem, this is 3V1. Because both are symmetrical, they have to intersect at the midpoint. Like this. Okay. This side is 3V1, is nothing but 3 itself. Now, out of this one, between L4 to L7 means from here it is valid. L4 to L7 only it is valid. This is also now minus. So, this is now dotted line, construction line, it becomes like this. Now, you see, having finished, you will find that it is like a straight line. Now, left out portion is the disturbed panel. Up to here already we have drawn. Up to here also, up to blue color line, up to here this is also over. For 6 panels 3, for 3 panels it is 1.5. Here we know, here we know. Only thing that we don't, this is in this panel straight line, in this panel straight line, in this panel straight line. straight line, straight line. In this panel also it has no choice, it must be a straight line. Having known the 2 points, you just connect them like this. This also now minus. So disturbed panel we connect it, simply end points you connect it, it will be done. Okay, this is your ILD for force in the member U3, U4. In this is a sign convention. Tension positive, compression negative. Positive quantities above reference line, tension. Compression means below reference line because we take it as negative. So this is what we have done. Connect remaining ILD between L3 and L4 as shown in figure. So like this we get the influence line diagram. Now what is the purpose of drawing this influence line diagram? When a unit load is moving from one end to the other end, the influence of that unit load on FU3, U4 is this shaded one. What this tells you is when the load enters the bridge, force in the member U3, U4 is 0. As the load is moving towards L4, force in the member is compression and gradually is increasing like this. It is now 1.5. That means at L4, if we keep a point load of 10 kilonewton, 10 into its influence is 1.5, 10 into 1.5, 15. 15 kilonewton is the force in the member U3, U4. Okay, so that's how the influence line diagram is drawn. Force into distance. Supposing that force is here, a particular location. First chapter in method of sections I told you, when the load is here, cut here, then look left side, V1 into 12, FU3, U4 is equal to so much. When you are taking it, you will get 15. When the load crosses, then what is the force? When the load crosses, for each location, instead of drawing forces in the members separately and wasting our time, entire variation in one graph we can show. Such graphs we have drawn in strength of materials also. Morse circles you have drawn. You have a small element subjected to Fx, Fy and shear stresses. Then on a plane 30 degrees plane you want to find shear normal stresses, shear stress say. Then you have one formula Fx plus Fy by 2 plus Fx minus Fy by 2 cos 2 phi. Okay. Now phi value 30 degrees means 2 phi is 60 degrees you will calculate. I don't want 30 degrees, I want 35 degrees. Then 70 degrees you have to put, again you have to calculate and waste the time. Instead of that, what you have drawn? Entire variation 30 degrees, 31, 33, 40, 60, 90. All the variations you can represent it with a circle. So any point on a Morse circle represents one state of stress on one particular location of the element. So on the element 30 degrees, if you want, here you have to rotate it by 60 degrees on the Morse circle, because formula is like that. So that circle is like a graph which will tell you the variation of the stress as the theta changes. On circle you have drawn, here you have drawn a graph like this. So this graph will tell you at different locations when load is there, what is the force in the member. Load into ordinate. Multiply, you will get force directly. Okay. So that is the purpose. Now when the load comes here, 1 is there means influence is 1.5 is compression. When the load moves from L4 to L7, his influence on U3, U4 gradually decreases to 0. Then it goes to the bridge, goes to the ground. What this force ILD tells you is, for all positions of unit load, force in the member U3, U4 is compressive. Such members we call them as pure compression members. They are always under compression only. Pure compression members we call it. Having understood that they are pure compression members, then you have to design. When you are designing them, you can put two channels or two channels with a plate or two I sections as a compression member, or if span is less, it's angle section. Depending on the magnitudes of the forces, those channels, angles we have to design. When you are fixing the design of compression members, from this you will get the force. load is there, load into this area of ILD, you will get force in the member. Once force is known, you factorize it, multiply by 1.5. That means UDL is moving, say, UDL into area of ILD. You get say 100 kilonewton. Multiply by 1.5. You design this member for 150 kilonewton. Then maximum slenderness ratio of this member should not exceed 180 as per IS 800 2007. In the design of steel structures, it will come the maximum slenderness ratio for compression member. This is for tension member. These members are subjected to reversal of stresses. For one portion compression, another portion it can be tension. Like that. So reversal of stresses you have to design. We will see that point. Now this is a pure compression member. So that observation will write here. For all positions of unit load, FU3, U4 is compressive. Such members are called pure compression members. Or simply compression members. Maximum slenderness ratio should never exceed 180 to prevent buckling. If the slenderness ratio is very less, 180 means it is more bulky. More slenderness ratio means if the member is more slender, more thinner. Compared to the length, cross section is so small that it looks like a slender member. Slenderness ratio will be more. Okay, like that. For these members, for compression members, slenderness ratio will be less. That means they are bulky so that it is very difficult to buckle. So this is how we will get the information for that. Now, second problem will reduce the entire write-up work. Because that simply wastes our time. In the exam, you cannot write load is left side, let me look right side. Load is right side, let me look left, let me look left side. That you don't have to write and waste the time. This is first time I am assuming that you are learning. I have written the sequence of your thought process. Now we will try to save the time. Okay. Now second one we want to draw ILD for FU3L4. Now we are interested in FU3L4. For the member FU3L4 also you have to cut it by 1 1. Load is somewhere here. Now look right side. Now we are interested in the diagonal member. We don't want horizontal. For them not to come into picture, if I write sigma y 0, these two will not have y component. So this I can find. So when the load is here, we'll cut it, look right side. Now, okay, if this is upward, to balance this upward force, now it has to be downward. This is F U3 L4, like that. Now we'll write that point F U3 L4. Cut it by 1 1. First point, load is between L1 and L3. We will consider equilibrium of RHS of 1 1, and we will now write sigma y is equal to 0. Only that will let you complete fast. So plus V2 minus, coming to this one, see here, this angle is 45 degrees. FU3L4 is acting downward but not vertically downward, inclinedly downward. So whose vertical component is FU3L4 sin 45 is acting vertically down. This is up. They should balance them, balance each other. So this is plus V2 minus FU3L4 sin 45 must be equal to 0. So from this you will get FU3L4 is equal to V2 by sin 45 means root 2 times V2, arrow mark is towards the joint, so compression. So draw ILD for root 2 V2 and consider between L1 and L3 only. Now you see, coming here, compression we got it. Root 2 times V2. So compression means it will go down. Root 2 times V2 means root 2 only. But out of this, up to here only it is valid, minus, because it is compression. This is only construction line. Okay. Now let us keep the load somewhere here. Cut it, now look left side. This is now second part. Load is between L4 and L7. Now you will consider equilibrium of LHS of 1 1. Again come here. Now same unit load has come here, somewhere between L4 L7, wherever it is, accordingly reaction we know how to calculate. Cut here, look left. V1 is upward. To balance it, it has to be downward. Again you see, this is and this is independent problems. You should not get a doubt that this is downward, how is it possible? This is one problem over. Another problem fresh, instead of solving a separate truss and wasting the time, here only we are managing. So this is your F U3 L4. This upward, downward when the load is here. Separate problem it is. Now arrow mark away, so it is tension. That means once the load crosses L4, force in the member U3L4 will become tensile. When the load is here, force in the U3L4 becomes compressive. Like depending on the load position, it can be tension or compression. So equilibrium of LHS of 1 1. Now here you will write sigma y is equal to 0. Upward positive, downward negative. Plus V1 because acting upward minus FU3L4 sin 45 must be 0. So you will get FU3L4 is equal to root 2 times V1. Arrow mark is away from the joint, so tensile. So draw ILD for root 2 V1 and consider between L4 and L7 only. L4 root 2 V1 means it goes now, we have to lift it up above reference line we are drawing because it is tension. So this line will go now something like this. This is root 2 times V1, nothing but root 2. Out of this one, L4 to L7 only it is valid. That means this area only it is valid. This is plus. This simply dotted line like this. Okay. So ILD this is over. Next point is this one, disturbed panel. So now that ILD has no choice other than coming from this point to this point, because between these 2 points it should be straight line. It cannot be a curve because between the 2 truss joints it is a straight line only. So this join these 2 points you will get something like this. So this is plus, this is minus. See here how much is ordinate here. For 6 panels root 2. For 3 panels 3 by 6 times root 2. Here for 6 panels root 2. 2 panels 2 by 6 times root 2. Like this. Now this is again ILD for F U3 L4. What is the sign convention? We will take tension positive, compression negative. This is the influence line diagram. Now what this influence line diagram tells you is when the load enters the bridge, force in the member U3 L4 is 0. As it is moving towards L3, force in the member U3 L4 is compressive. When it is at L3, that compressive force is maximum. When the load is further moving somewhere at this location on the rail, not on the truss member, on the rail somewhere here it is there, load into the ordinate here it is 0. So force in the member U3L4 becomes 0. When the load further moves to joint L4, immediately force in the member U3L4 will become tensile and maximum. Then from when the load is moving from L4 to L7, his influence on U3L4 gradually reduces to 0. After that load goes to the ground. So this is the influence of a single unit load on the force U3L4. When unit load influence, if I know if a 10 kilonewton load is moving, I can find its influence. If UDL is moving, I also can find what is UDL. Uniformly distributed load is nothing but infinite number of point loads. So many point loads are there. What are their influence on the member? We can find intensity of UDL into area. We have to write. So what this suggests is, in a day, supposing that 1000 times trains moved from here to there, from there to here, then 1000 times force in the member U3L4 changes its direction, compression to tension. That means 1000 times this member will be compressed, pulled, right? That is called stress reversal. If any member is subjected to reversal of stress, it can be upward shear, downward shear, compression or tension. So stress direction, if it changes, we say that the member is subjected to fatigue. Fatigue means it is a process wherein the member strength decreases if it is subjected to reversal of stress. That property of the breaking of the member when subjected to reversal of stresses, or the property of losing its strength when subjected to reversal of stresses, we call it as fatigue. So when you are designing such members, you have to take the fatigue coefficients also, and accordingly bigger one you have to size you have to increase slightly. Because if you are designing it for 100 years span, 100 years, let us say, in 100 years the stress reversal can be 1 million times, maybe 10 million times. So such cases 10 million times means accordingly fatigue coefficients you have to take and design the member accordingly. This member is subjected to reversal of stresses because of the live load. Live load means train loads. When their train loads are moving, stress reversal means there is a likelihood of compression due to live load. Whenever there is a compression, you have to compression only predominantly will be acting. Means compression only is more dangerous because of buckling. So you have to design it as a compression member and check for tension also. Naturally it will be safe, though it is slightly more force also. If it can take, a member can take compressive force of 100 kilonewtons, say, it can take tensile force of at least 300, 3 times more it can take. Because permissible compressive stress, if you take say 100 or 100 Newton per mm square, at least then in tension permissible stress is 220 like that. That means at least 2.2 times it can take more load. So accordingly, if it is safe in compression, generally it will be safe in tension also. If the force variation is not that much, it will be safe in tension. So the code book tells you that the slenderness ratio for such a member which is subjected to reversal of stress due to live load, slenderness ratio should not exceed 180. Okay. So those points will write. Now in this case, connect the remaining ILD. Connect remaining ILD between L3 and L4 as shown in figure. Okay. Now you have understood the process. We'll write that note. In the exam, they simply ask you sometimes the observation itself. For an N-type truss, the diagonal member, when the load is moving from left to right, force in the member in a 6 panels, force in the third diagonal changes from compression to tension or tension to compression, tension, always compression, like that. Then based on the description, first you have to draw ILD and observe. It is changing from compression to tension. So entire story we will not write. What is to be written we will see from next problem onwards. Because load is left side, let me look right side, we cannot write. That we have to visualize. Then accordingly only two equilibrium equations we will write. Okay. In the exam, this story we will not write, only this line is important, that's all. Like this, two equations we have to write. See here now, note for this one. As the unit load moves from left to right, FU3 L4 changes from compression to tension. That is one of the options, compression to tension. Such members are called members subjected to reversal of stresses. If a member is subjected to reversal of stress due to live load, LL means live load, due to live load, maximum slenderness ratio is 180, because the compression only is very high. Buckling is a very big problem. Okay, next. Okay, now let us see one more member, U4L4. Third one is ILD for force in the member U4L4. Now you see, U4L4 means you have to cut it. How shall we cut this U4L4? If I cut like this, 1, 2, 3, 4 are cut. We should not cut 4. If I cut like this, 1, 2, 3, 4 are cut. Again problem. So, you see the member configuration at the joint U4. 1, 2, 3, 2 are in line. So, force in the third member is always 0. So, ILD is simply a straight line you will get for this one, telling you that for all positions of the moving load, force in the member U4L4 is 0. This is ILD for F U4L4. That's all. Simply a straight line you will get. Means wherever unit load is there, U4L4 is 0. This is the one. For all positions of unit load, FU4L4 is equal to 0. Why? Because of member configuration at joint U4. That means like this. This is U4, This is F U3 U4. This is F U4 U5, and this is F U4 L4. If three members are meeting at a joint, two members are collinear, force in the third member is 0. Okay, because of that. So draw ILD as a straight line. Straight line as shown in figure. Like this. That means if you see the joint configuration, member configuration, 4 options they give. Which option has straight line you see and tick it. It takes only 10 seconds time. Now, I want to draw this over. I will draw ILD for F U1 L1. If I want to draw ILD for F U1 L1, you have to cut it first. So cut it like this. This section, let us say 2, 2. Cut it by 2, 2. Now disturbed panel is L1, L2. In the disturbed panel, don't keep the unit load. So other than the disturbed panel means L2 to L7 single case. So only one case you have to deal with. Keep load somewhere here. RHS of 2 to keep the load, look left side, LHS of 2, 2. LHS of 2, 2, it is like a method of joints problem. There are two members meeting at one point. It's a method of joints. So using method of joints, find force in the member U1, L1. You see here, V1 is upward. To balance it, it has to be downward. So for all positions of unit load from L2 to L7, force in this member U1, L1 is compression. Then only it will be in equilibrium. Like that. So that we'll write now. ILD for F U1 L1. First what we have to do is cut it by 2, 2. Load is somewhere between L2 and L7. Between L1 and L2 if load is there, you cut it say. Part of the load is at L1, remaining part is L2. Whatever side of the section 2 do you take it, part of the load you have to deal with. But we don't want to deal with that headache. So unit load we don't want to deal with, so that our expressions will be simple. Okay. So load is somewhere between L2 and L7. You will take equilibrium of LHS of 2, 2. You take now sigma y is equal to 0. Upward force is positive, downward force is negative. Plus V1 minus FU1 L1 is equal to 0. So you will get FU1 L1 is equal to V1, arrow mark is towards the joint compression. So draw ILD for V1 and consider between L2 and L7 only. Now this is over, already we have finished. Fresh diagram we are drawing for U1 L1. What you got was V1. So V1 we know how to draw. Remove the support, hold it, pull it down because it is compression. If it is tension, remove the support, lift it by 1. The deflected shape of the beam, an imaginary beam, itself is the ILD for V1. So now we are pushing it down by 1. V1 is equal to 1. So we will join it by a straight line. Out of this, we have to consider up to here only, L2 to L7. This is minus, this is imaginary line. Remove that line. Like this. For 6 panels, 1, 5 panels, 5 by 6. This is the point. ILD for V1 means it is like simply supported beam, simply supported truss, same. Reaction, when you are drawing ILD for reaction, remove the reaction, lift it by 1. The truss or a beam. If you have a beam, straight line will go like an inclined line. If a truss will take up inclined shape only. Assume that this is a truss. Remove the support, lift it up. The truss will take a shape of inclined one. So, inclined shape. So, truss you can imagine that it's like a line. So, line will take a triangular shape like that. So, to push it up or down, it depends on whether it is tension or compression. If the force in the member is compression, remove the support, pull it down so that you will get negative because you want to take compression negative. Supposing that force in the member you get tension, V1 tension. Remove the support, hold it, lift it by 1 so that it goes above reference line. So, plus like that. So, depending on the sign conventions, you can lift it up or down. Take tension positive, say. So, lift it up. Tension itself is negative, so push it down. Our choice. So, this part is over. Up to here we have done. Next, when the load is somewhere disturbed panel, how to connect? This panel, how to connect? See, last panel, you see how you are connecting. When the load is exactly at the support, so influence is always 0. So is the case here, influence is always 0. When the load is exactly at the support, force in the member U1, L1 is 0. Then who will take that one? Entire load directly transferred to the support and V1 is 1. So they balance each other. U1, L1 simply keeps quiet. So it will be 0. That means you have to connect it as a straight line like this. Minus. So this is 5 by, this is ILD. ILD for FU1, L1. Again, you see this end member also pure compression member only. Tension positive, compression negative. So here you have what we have to do, connect remaining ILD between L1 and L2 as shown in figure. Now we'll see what when the load is exactly at L1, what happens, let us see. When the unit load is exactly at L1, FU1 L1 is 0. Why should it be 0? Why can't it be 1 itself? So this is the truss, let us say. Okay, this is V1, this is the ground, this is L1, L2, etc. This is U1, U2, etc. Now, as I told you, here there is a cross girder, here also cross girder. When load enters the bridge, say, it enters the bridge on the cross girder because it's moving on the rail. So first it enters the cross girder. Entire load is taken by the cross girder and transfers to the truss joint. And that truss joint is resting on the support itself. So cross girder directly transfers load to the support itself. So here there is a, suppose unit load 1 is there, that one is resting on the rail, rail is on the cross girder is resting on the support because first entrance point there is a cross girder, load entered on the rail and rail is resting on the cross girder, cross girder is resting on the support. So directly it will transfer to the support. So V1 becomes 1. Then on the above the cross girder there is a member, so that will not take because cross girder is resting on the support. Directly support will take it. If it is in air like this, then cross girder first transfers load to the joint, then that no support is there here. So whatever load is hanging, that is taken by the members only. But whereas here when enters the bridge, load is not taken by the members. Load is directly taken by the support. So these two balance themselves. Such cases, now here in this one, if U1, L1 has to be 0 because they are already in equilibrium by themselves. Downward one, upward one, they balanced. But if load is here, say, then what will happen? What is there here? Load here means rail is here. On the rail, when load is here, part of the load goes to this cross girder, remaining load goes to this cross girder. Whatever load that goes here, that is directly transferred to the support. Suppose load is at the center, say, 0.5 is directly transferred, V1 is 0.5. Now here, L2 joint takes 0.5. Because of 0.5 here, force in the that 0.5, some portion of this will take, some portion the other vertical member will take on the other end. Supposing that out of this 0.5, this is taking 0.1, that means when load is acting, it takes 0.1 and transfers, say. Already existing 0.5 is there, this 0.1 put together upward reaction 0.6 you will get. Then the here other end 0.4 it will transfer, like that. So that is the meaning of that. Once load crosses the cross girder only, the truss starts taking the load. Also, in strength of materials you have studied, supposing that you have a beam like this, say, and when the load is here, suppose 1, then reaction directly V1 becomes 1 only. This simply keeps quiet. So is the case here on this side also. Support. Now beam simply keeps quiet. But load comes here, say, then part of the load goes here, remaining goes here. So it's like this. That free body diagram. This is over. Now, if at all, this is the beam, load comes here, say 1. Then part of the load goes here, here 0.5, here 0.5. Then the support is there here. This will react by 0.5 upward, 0.5, like that. So beam will, out of 1, 0.5 is transferred here and here. So this beam will press this support with 0.5 down. So this will not keep quiet, it will resist upward by 0.5. So that's how the reactions will develop. Whatever force with which this beam presses this column or support, with the same amount it will exert a reaction. First the beam has to press it. If it doesn't press it, that will also will not do anything, like that. But without the beam, if direct load enters the bridge here, say, then direct transfer, this fellow simply keeps quiet. Similar to that arrangement is there in the trusses. Instead of like this, there is a cross girder directly resting. So it will be transferred to the support directly. So that's why that type of triangle comes. Okay. So I think now that strength of materials, you have known how the load transfer mechanism is. Now ILD is for force in the members of bar and truss, that